Welcome to the lecture video for section 2.6 in the textbook. And this is where we start talking about probability. So I'm excited to do this video with you. It's the first real application that we'll see in this class, and it's an important one. Probability is a really advanced area of math at this point in the modern world that most people consider it a separate area of math. And really, I mean, probability and statistics are a completely separate branch of science than math is. It's advanced so much, and it's really due to many of the concepts that we've learned along the way that we can even state some things about probability. We'll see how the calculus, especially integral calculus, some of the techniques we've learned in this class already factor in. You can see a little preview picture here of what's going on with using the area under a curve to approximate some value. And the value in this question, in this particular picture, 0.82, will represent some probability, about 82%. So already just in the preview, you can see there's going to be some fun calculus involved. But the main goals that we'll cover in this lecture are to test the properties of a probability density function. And first, we have to define what a probability density function is, but one is pictured right here. That's a PDF. Next, we'll understand how to use the probability density function to describe the underlying random variable. We'll also have to set up what it means to have a random variable, and then what the probability of that variable taking on certain values is. We'll be able to use our function and integral calculus to study that further. Next, we'll learn about three specific types of random variables and their distributions. These are called the uniform, exponential, and normal random variables, and the same names for their distributions. And finally, we will learn how to actually compute probabilities for all of these random variables using their distribution functions. And we'll learn how to compute things like expected value and the median through a couple examples. Expected value, you might have also heard called the mean of a variable or the average of a variable. That will have a specific meaning using the integral of a PDF, a probability density function. So let's get started. So to begin, here are a few just motivational reasons why we might study probability. And mainly, we'll kind of rely on the importance of statistics in the world and say, look, this is a good enough endeavor to focus on some of the underlying math in this class that hopefully you'll get some new understanding of just by studying things this way. So the point of statistics from my point of view is to make inferences about sets of data. And as we go further in the course, we'll see more and more applied problems coming from this world. So if we want to make inferences about some imperfect set of data out in the world, we need to first be able to understand probabilities of selecting from that set of data and making inferences. And we really want to understand how likely it is for the inference to be correct within a certain error threshold or tolerance. So the basic model for performing this type of statistical analysis or inference is to first assume that the type of pattern that we're looking for does not exist. This is typically called the null hypothesis, and it goes something like this. Oops. So the null hypothesis might be that there are no students in this class over 6 feet tall. And if we're looking for students over 6 feet, and maybe this class is too small of a sample size, but we could say there are no students at Emory over 6 feet tall. The null hypothesis is the opposite of what we're actually looking for. And then what we'll do is we'll collect observations among maybe everyone in this class. There are 40 people plus me and 2 TAs. So let's say among 43 people, we can collect their heights, and then we can compute the probability of actually seeing those observations, given our assumption. In our class, it would be easy to see if there are any people over 6 feet tall. If we wanted to study this for the entire population of Emory, there are no people over 6 feet tall, we wouldn't have to collect every piece of data to make some inferences about the likelihood that there are some people over 6 feet tall. As we make more complicated statistical assumptions or make more complicated null hypotheses against those assumptions, such as 10% of the population is over 6 feet tall. The null hypothesis might be 10% of the population, or less than 10% of the population is over 6 feet tall. Then we'll start to extrapolate from larger and larger data sets to confirm or confirm the null hypothesis, which is against our expectation, or to confirm our actual observation that we're making. If the probability is very low, we have to understand how to compute probabilities given this type of set of data, then the assumption we make is probably false. And if you go on and study more statistical analysis beyond this class, you'll learn about things like p-values, which we might talk a little bit about later. But the p-value is a probability assigned to the event that a particular null hypothesis is proven false. Now, it's a little hard to unravel that sentence. There's a lot of negations in it. But if we make a null hypothesis, we're saying what we're looking for is not going to happen, and then we'll assign a particular probability that that is incorrect. This is just the way things are done, but the punchline for us is we want to be able to make statistical inferences by computing probabilities. And you can study all of these things further in other courses. I encourage you to go take a statistics course, no matter what field you're going into. It's really good. It's a really good different alternative way of understanding the world from your intuition about statistics, which might not always match up with reality. So let's define what it means to have a random variable. In math, we like to give things names and then study those things based on the properties that their definition encodes. So for us, a random variable will be an abstract system for keeping track of the event of a particular, or the outcome of a particular event or a series of events. So it's a little abstract, but a random variable typically means we're performing some experiment or performing some series of observations, and the variable is a counter, maybe on our computer or just on our notepad with a pen and paper, that we record the different outcomes of randomly selecting from the possible event space. So we'll use the notation p parentheses blank to denote the probability that a particular outcome occurs. And you can think of p like a function that inputs potential outcomes to performing an experiment. And there's a really classic example in a moment that we'll go through, but think about things that have a probability, like flipping a coin, rolling a die, or selecting a ball out of a bucket of a certain color, or balls of different colors and selecting one of a certain color, or your favorite t-shirt out of your drawer without looking in the drawer. These sort of things have a natural probabilistic interpretation. So you can think of p of blank, p parentheses blank, as a function that inputs a particular outcome we're interested in studying further, and it outputs the percentage probability, or a decimal from 0 to 1, of that event actually occurring, given a random selection. There are two basic requirements of p as a function. I'm going to stop calling it a function now. We'll actually have functions that do different things in a moment. But p as a probability expression has to satisfy at least two things. If something cannot happen, if it's impossible for a particular event to occur, then its probability has to be 0 or 0%. We'll write everything as decimals, but this is 0.00. If something is certain to happen, then the probability of that outcome is 1 or 100%. And that's basically the only rules. There's another subtle rule, which is if two events are independent, if they don't influence each other's likelihood of happening, then the probability of either one happening is the sum of the probabilities of each individual event. And this is actually what gives probability a lot of mathematical power. But before we get into some deeper concepts with probability and density functions and things like that, let's talk about this basic example. So our outcome in general can be just the result of performing an experiment or performing a certain action some number of times with a probabilistic pattern to it. And the outcome could be interpreted probabilistically, or we're asking what are the chances of something are happening, maybe in plain terms. So here are actually two classic examples coming from game theory. If we roll two six-sided dice, like in Monopoly, for example, do you roll two dice? No, now I'm forgetting. I think you roll two dice in Monopoly. Or in craps, for example, if you roll two dice in a lot of gambling games with dice, and we ask for the sum of the two dice to be a number, it'll be a number from 2 to 12, if you think about how to add up the total dots on two different dice, then we'll call S, the random variable S, the sum of those two dice rolls. So how do we actually compute probabilities? Well, among all of the 36 possible outcomes, there are 6 outcomes for one die, and then another 6 for the other die. So there are 36 total possible pairs among those two dice. The probability of getting a particular sum can be written as a fraction or as a decimal from 0 to 1. In this case, it's easier to write fractions since there are 36 outcomes, and the total number of ways of getting an 8 as your sum of two die rolls or 2 dice rolls, there are 5 different ways of getting an 8. It actually helps to draw this, which I'm not going to do, but I encourage you to either take out a pair of dice if you have some at home and flip them around until you see all 5 ways of making a sum of 8. Or if you just write down the numbers 1 through 6 and try to pair them up and get 8 from their sum, you'll see that there are 5 ways of doing it out of 36 total possible rolls. So that means when you roll 2 dice, you have a 5 out of 36, or as a decimal, that's about a 14, it's just under 14% chance, about 13.9% chance of getting an 8. More interestingly is if you want to get a sum of at least 8, for example, if you're playing a game where you want to move further or get higher rolls, you can actually add up all of the probabilities for those different rolls, add them together, and that'll give you a probability of anything happening over 8. Another example, which I think is even easier to study, there are only 2 outcomes in this, is the number of tails when 2 coins are flipped. And I should say there are only 2 outcomes per coin. With coins, there's heads and tails. We assume that there's a 0 probability of the coin landing on its side and not flipping down on either side, and it's also a fair coin. And so when I flip 2 coins, there are technically 4 outcomes. Maybe if they're colored differently or they're 2 different denominations of coin, you can say the left one or the right one to be even easier. There's a head or a tail on each coin, so there are 4 total outcomes, even though 1 head, 1 tail seems like the same outcome. Because there are 4 different options, and we assign assign to the letter T the random variable, counting the number of tails among these 2 coins, there are either 0, 1, or 2 tails that can show up. And if you want to ask for the probability that T is greater than or equal to 1, or in plain English, the probability of flipping at least 1 tail with 2 coins, that probability is 3 out of 4. There are 4 total outcomes, and in 3 of those options, there's at least 1 tail in the mix. So to make things more mathematical, we can encode probabilities with something called a distribution or a density function. I'll use all of these terms interchangeably, and now when I say function, I'll typically be referring to this type of function. So what is a distribution or a probability distribution function? In simple terms, a function like this describes at each input or each potential outcome A, the probability that that outcome occurs. So remember that we're thinking of capital P, the probability expression, as something that inputs particular outcomes or events and outputs the probability of that event happening. So notice that outcome and output have the same prefix, but those are actually playing different roles in this function. So an event, which maybe I'll try to stop calling it outcome, is the input, little t, and the output of the function is the probability that that given event that we plugged in happens. So for the number of tails on 2 coin flips example, that was our capital T variable. The distribution function for this is actually pretty easy to write down. If we write all of the different potential outcomes or events that T represents, it's the number of tails. There's either 0 tails, 1 tail, 2 tails, and actually anything else is impossible. So we'll assign that a probability of 0 right away on its bottom line. For each of those remaining possible outcomes, 0 tails, 1 tail, or 2 tails, we can assign each of them a probability. If you go count all 4 options and assort them in these different buckets, you'll see that a quarter of the time, no tails show up. That means there have to be 2 heads equivalently. Half the time, exactly 1 tail shows up, and then the other is a head. And the remaining quarter of the time, exactly 2 tails show up. Notice a few things about this distribution function. First, and maybe most importantly for us in this lecture, the sum of the probabilities, or the sum of the total values that this function spits out, adds up to 1. These outputs add up to 1. And that includes all of the zeros that we assign to any impossible T outputs, T outcomes. Also, in this case, there are only finitely many values of T that are possible. And I should say this again and emphasize that this is finitely many values of capital T. So capital T, again, is our event random variable. It's telling us possible outcomes to performing some action some number of times. In this case, flipping a pair of coins a single time or flipping one coin twice, recording all of the results. We'll call that a single event. So there are only finitely many values of t. There are only finitely many things that can happen in this experiment. Either we get both heads, one of each, and there are two ways of doing that, or both tails. What if we wanted to model something like height that we mentioned earlier using a random variable? So here's where things get tricky, but actually get maybe more exciting for us since we're used to studying situations like this in calc class. If we want to model height, maybe we'll put everything in terms of inches to have consistent units. Well, if you think about it, no one is exactly blank inches tall. For example, if we pick 5'8", that happens to be my height. No one is exactly 68 inches tall, although people certainly round up to the nearest inch. But if you took a very, very fine, maybe a laser measurement device and rounded to the nearest hundredth of an inch, you'd have some cutoff values, but you could even keep rounding and rounding and rounding for more precise estimates and say that the actual values that a person's height can take on, the actual height that a person can have, can be anywhere on a continuum of possible values. So no one is exactly 5'8", even if I report that on my driver's license, but everyone's slightly taller or slightly shorter, and we just sort of don't care about the difference for practical purposes. However, if we want to model things like probability, we do want to be as fine-toothed as possible with our distribution function. So using something like a distribution function that we had on the previous slide with a finite number of outcomes would be unsuitable for this situation. And basically because if we count up all of the possible outcomes, there will be infinitely many, and there will be more than just infinitely many. There will be a continuous intervals worth of possible outcomes. All of the heights from, maybe from 0 to, I don't know, 8 feet. I actually don't know the tallest height of a person in the world in recorded history, but let's say 8 feet is the max, or that's probably higher, taller than anyone has ever been. So from 0 to 8 feet, there are infinitely many values in between if we allow infinitely many decimal places for the heights in inches in between. And if we count all of those up, that would be the denominator of our fraction in the previous example. And if there are infinitely many, the fraction is going to be 0. So all probabilities will be 0. And that's not what's supposed to happen with probability. So instead, we're going to use something called a continuous random variable. We'll denote these by capital X rather than capital S or capital T on the previous slide. So capital X, a continuous random variable, is a random variable. So it's some abstract counter who's keeping track of outcomes of a process or an action taking place. The outcomes here are real numbers. And the probability of such a variable is modeled by a continuous probability density function. This is where continuous random variable comes in. So it's modeled by a probability density function, f sub capital X of x. It's a function of little x, where x can range along those real numbers, potentially over the entire real number line. And for an input little x, which is describing a possible event in our experiment, in our continuous random variable, f of x tells you the probability of that event occurring. And the way that it tells you that is actually as follows using an integral. So if we pick a possible range of values for our random variable, we pick a range of heights, for example, from 5'8" to 5'8.5". Those are maybe A and B here. The probability that our true height of a given person lands in that range from A to B is actually given by integrating the probability function f sub x. So we integrate from A to B, those ranges that we're in, the range of x values we're interested in, of our probability density function f over with respect to dx. There are two things that a probability density function must satisfy, other than this definition that it captures probability by integrating. First is that the function must be non-negative for all inputs x. So if you think about this graphically, a probability density function always has to be above or at the x-axis graphically. Another important property, and again, I would call this the most important property for probability functions, property 2, is that the integral over the entire real number line from negative infinity to infinity of this function has to be 1. So I want to point out two things here. It has to equal 1 for the same reason that we want all of our probabilities for a finite situation like coin flips and die rolls to add up to 1. The total probability of anything possible happening is 1. And for a similar reason, the integral is keeping track of adding up all probabilities for a continuous random variable. The other thing I want to point out is this is an integral from negative infinity to infinity. And this is exactly why in the last lecture we learned about improper integrals. So we're already going to put those techniques to use in this lecture. Here's a picture to keep track of what's going on visually. And this is, I encourage you to keep this graph in mind anytime you do any type of probability calculation. So if we have a variable x, a continuous random variable x, and we know its probability function f has, some graph. This kind of looks like a bell curve, which we'll learn about later in this lecture. Then integrating the area under this graph, and now it is a true positive area since the function is always non-negative, tells you over that certain region what the probability of the outcome falling in that range of values is. For example, in the picture, you see on the x-axis, the values 60 and 68 are highlighted in blue. And the integral from 60 to 68 of this probability function is apparently 0.82, or about 82%. Given an 82% probability, what this says in terms of the probability and its associated random variable is that we expect 82% of measurements to fall within 60 and 68, whatever units are described here. If these are inches, then we expect maybe in whatever population this random variable is describing, 82% of people's heights to fall within 5 feet and 5'8". Which that seems like a high probability in my experience, but maybe I just know a lot of tall people. So I don't know. This is an interesting question. And if you ever read statistics out in the world now, 40% of people in a certain population have a certain whatever demographic or physical attribute, or voted a certain way or anything like that. I would say pretty much all of the time those types of large population statistics are extrapolated using this type of statistical inference, using a function that's generated from some set of data that actually isn't the entire population. Here's an example, and let's actually work this one out together. We know how to perform integrals, and in this case, we'll set things up and compute the integral to study the particular random variable. So let's suppose we have some continuous random variable x, where whatever its outcomes are, their probabilities fall under the following probability density function. So they're described by this function, f. So I'm probably going to stop saying f sub x of x because there's a lot of x's. I'll just say f of x, or just f. So the function f in this case is between 0 and 3 given by 1 over 9 times x squared. And for any values outside of that, this function will take on the value 0. So this is apparently a probability density function. In order to be a probability density function, we actually have to verify a few things. So it represents this random variable in the sense that when we integrate the function, it'll tell us about probabilities. That's sort of cooked into its definition, but we have to verify that it's always non-negative and that its integral over the whole real number line is 1. So those are the two things that we're going to check together. You are perfectly capable of doing this on your own. And if you want to flip back a couple slides to remind yourself of those two criteria, then go ahead. But I encourage you to pause right now and at least check one of them, that the function is non-negative for all real inputs, and that the integral from negative infinity to infinity is equal to 1. Let's do it together now, though. So how do we check that something's non-negative? Well, we can pretty much eyeball this, and I'm not going to write anything for it. For any values outside of the interval 0 to 3, the function just takes on the value 0, which is not a negative number, so we're good there. And for values between 0 and 3, notice that the function is 1/9 x squared. That's always positive or 0. So at x equals 0, that's 0. Everywhere else, this is a parabola above the x-axis. So our non-negative property is good. And now what we really need to do, and usually this is the case, it's easy to check the first property, is we want to integrate our function from negative infinity to infinity. And try to exaggerate, this is a capital X dx. And what's really going on here with this function is outside of a certain finite interval from 0 to 3, the function takes on the value 0. So if you wanted to split this up, I'll quickly sketch it and then just erase and go back. We could integrate from negative infinity to 0, from 0 to 3, and then from 3 to infinity. But what's going to happen for these on the outside, the function takes on the value 0 for all of those input values. So the integral of the 0 function is still 0. So all we have to integrate here, this is a nice thing about integrals, which is why they provide such a solid foundation for probability, is we only have to restrict to where the function is non-negative, or sorry, where the function is actually positive. So in this case, on the interval 0 to 3, we're going to integrate the function as it's described above. For those input values, the outputs are 1/9 x squared. This is a power rule problem, so you've probably already finished this while I was talking. This is let's see, 1/27 x cubed from 0 to 3. If I plug in 3, I get 27 over 27. There's our 1. And if I plug in 0, I get 0. So we got an integral of 1, which means that the total probability captured by this function is 1. That's what we want to happen. Something happens 100% of the time is usually how I think about this. Okay, so part B of the problem said to compute the probability that this random variable took on a value at least 2. So remember, the function is described piecewise like this. And for any values above 2, we want to integrate from 2, in this case, all the way up to infinity. That captures all of the x inputs above 2, or greater than or equal to 2. And we want to just integrate its probability function to compute this probability. So this is the name of the game with computing probabilities. We convert the p parentheses event into an integral of the probability density function f. That's always the first step for computing probabilities in these continuous situations. So again, what happens when we're above x equals 3, all of the function values are 0. So we can actually reduce this computation. We didn't have to do an improper integral yet. We will in a few problems during this video. We only have to integrate from 2 to 3 here. And again, the function's name is 1/9 x squared for values between 0 and 3. It's the same exact antiderivative, 1/27 x cubed, except we're integrating from 2 up to 3 now. So let's see what happens. We will get 27 over 27 is 1 again, and then 8 over 27 is going to give us a total probability of 19/27. And I don't know about you, but I like thinking of these as fractions and decimals if I can. This is about, let's see, 70.4%. I'll write it as a decimal just to keep things consistent. Okay. Here's an interesting question. So what does this function and what we just learned from our, mostly from part B, what does this function tell you about likely values of x? I want you to pause the video and write out some of your observations based on what we just computed for this function. We know that all of the values, any possible outputs of this variable, have to occur between x values of 0 and 3, because 100% of the outputs happen there. We also learned that approximately 70.4% of the time, the outcomes occur between x values of 2 and 3. So those are things we learned. What does this tell you about the likely values of x? And can you predict what this distribution looks like just based on these couple observations? So now I'm going to switch back to the slides and let's keep pressing on and learning more about probability density functions. Okay. By the way, here's a graph of that function generated using a computer. And the gold shaded region is the probability we just computed. It's about, so they use equals, it should be an approximate symbol. It's about 70.4% of the outcomes of this variable occur in that chunk. One way to answer part C of the last problem is to say that larger values of x on the interval from 0 to 3 are more likely to happen. And you can see that this is a parabola, it's a quadratic function. As we increase the x value, as we increase that number assigned to different outcomes of the experiment, the graph jumps further up. It goes up quadratically. So larger values from 0 to 3 are more likely to happen. And larger ranges of larger values will have a higher percentage of the total area, which is 1 under this graph. Here's some main takeaways from this problem in our discussion of random variables so far. So the first thing, and you'll be asked to do this on many problems in this class, is to verify that a function is a PDF, probability density function. And in order to do that, you need to check that on one hand, it's always a non-negative function, never spits out negative numbers. And on the other hand, that it integrates to 1 over the entire real line. In many instances, this entire real line integral will reduce to a finite interval like our previous example, but it's possible, and we'll see examples in this video, that we do have to integrate a double-sided infinite integral, meaning an improper integral that we learned about last time. We can compute probabilities for a given continuous random variable using our PDF little f, and by integrating that function over the given interval of values that we're interested in. And where the function is large, meaning it has a higher height, the outcomes in that range are more likely than where the function is smaller, has a smaller height. For example, here's the graph of the same function. If we pick a range of potential outcome values between 2 and 3, they are more likely to happen than the same spread of values are centered around 1. So these have the same width, but the areas that are captured by the graph, and therefore the probabilities of these outcomes occurring in these ranges, are different. They're much more likely in the upper range of values than in the lower range, just because of the way this function is shaped. By the way, this is a function that we chose to study, but we didn't really attach it to any real-world probability problem or any real-world experiment that we're performing. And really the trick is, out in the world, if we have a particular application, to find a function that accurately describes its probability. We were able to do that for the simple examples of flipping 2 coins or rolling 2 dice, because there were only a finite number of outcomes. And in general, it's a difficult challenge to come up with an accurate probability function that will compute probabilities for you. I want to study 3 examples with you in this video that are some of the most important examples in all of probability theory. These really form some of the core foundational tools for studying more complicated distributions later. So the first one, and I would call this the simplest, kind of the baseline example of a probability function, is what's called a uniform distribution. So there's a function formula for this distribution. It's given by 1 over b minus a when we're in between the values a and b, and it's 0 outside of those values. As a graph, it's just a rectangle with height 1 over b minus a and length a to b. In this particular graph, the a and b values are 2 and 5, and that would mean that the height is 1/3. You can see it's basically drawn to scale that way. On any given interval of values a to b, there is an associated uniform distribution, which is just this exact function. You plug in 1 over b minus a to compute the height of the rectangle. But more importantly, what does this probability function mean? What does a variable having a uniform distribution actually behave like? Well, if you think about it, if we were to integrate this function, and you can actually do this to practice testing the different techniques with the probability distribution. Any values in a certain range of a given length will have the same probability as any other values in a same sized region or a same length interval. For example, the probability that in this uniform distribution that the variable takes on a value from 2 to 3 is exactly the same as the probability of taking on the value from 4 to 5. So a 1 unit length interval has the same probability no matter where it occurs in the distribution. Contrast this to the previous quadratic example, where the further towards 3 we moved, the higher likelihood of those values happening was. So here, uniform means everything has the same likelihood. It's like asking not for the total number of tails with 2 coins, but for a single coin, the outcome to be head or tail. Now there's an equal likelihood if it's a fair coin, just like there's an equal likelihood of a particular number showing up on a single die. Those are uniform distributions. They're just they're not continuous ones. There's only a finite number of values. Here we can have any value in between a and b occurring, and it occurs with an equal likelihood. And in practice, what that means is the distribution looks like a rectangle. Here's another type of distribution, which on face looks more complicated, but is actually pretty useful in many applications. So suppose that some event happens randomly and uniformly, but not uniformly over all potential values like it did in the previous problem, but it happens uniformly at a certain rate. So suppose an event happens randomly, but in given amounts of time, we know that it always happens an average of lambda times per unit of time. So our units of time will be x, and the event happening will be recorded by some number lambda. This will be an integer, and it'll tell us how many times in a given unit of time that event happens. For example, let's say that I have an alarm set on my phone so that every hour it goes off 3 times. It happens 3 times randomly, but we know that in an hour it's supposed to go off 3 times. Maybe this is to keep me on track when I'm getting distracted by the internet, or for some other reason I need to check in on my dogs 3 times per hour, but it doesn't matter when they happen. This is sort of a contrived example, but you can imagine asking, what is the expected amount of time before the first alarm rings, given that it has to happen randomly and in 3 times per hour. A more practical version of this example would be if we know that people will be taken care of at the register at a restaurant or at a store a certain number of times per minute, but it's random depending on how long each customer takes. There's an average expected wait time, and if you jump in the back of the line, you can ask, how long am I expected to wait to get to the front of the line and be helped at the register? This is actually a problem that can be modeled using an exponential distribution like this. But to keep things simple, I like to think of something happening 3 times in an hour. It's a big chunk of time, but it's 1 unit of time. And we can ask about its expected probability of happening in smaller time intervals, such as the first 20 minutes. This is modeled by something called an exponential distribution, which as a function is, there's actually a typo on this slide. Let me just highlight, this is supposed to be the other direction. So for x values less than 0, the function takes on the value 0. You can think of this as x is a time variable. So we'll start the stopwatch at time 0. And then for all values, oh, sorry, this is not a typo. For x greater than or equal to 0, I just read it backwards. So for x values starting at 0 and going off to the right, the probability function spits out lambda e to the minus lambda x, where lambda is that number of times that event occurs on average per time unit. Here's a depiction of a graph of one of these functions, and if you go to the interactive versions of these slides, you can see the little widget allows you to change the lambda value, and you'll see that the function moves up and down depending on what lambda is. So here are a couple observations about an exponential function. So if lambda is larger, or the event is expected to occur more times per hour or more times per time unit, then x is likely to be smaller, meaning the wait time is likely to be smaller. If my alarm on my phone goes off instead of 3 times per hour, 6 times per hour, then it's more likely that I don't have to wait as long. So the x variable, the outcome of how long I have to wait, is smaller on average, as the event is expected to occur sooner during that time interval. Next, the probability of the event occurring in any given interval, given that it did not occur before that interval happened, only depends on the length of the interval. This one's a little hard to wrap your head around, but I encourage you to write this down in slightly more mathematical terms. We're saying the probability of something happening in a given interval, so that's p, that the x variable is between a and b, given that it did not occur before that interval, and then depends only on the length of the interval, so the expression should just depend on b minus a, in other words. You can write this one down to practice. All right, here's one more type of distribution. This is the last one that we'll study in this lecture. It's called the normal distribution, but I want to immediately give it its more famous name, that it's called a bell curve. So a bell curve, and we saw one picture of this already, I'll show you another in a moment, is in mathematical terms a normal distribution. It's a type of probability distribution. And what's so important about this is that so many things out in the real world that can be described statistically and probabilistically can be modeled using a normal distribution or something related to a normal distribution. So the downside of a normal distribution, the upside is it describes a lot of things, whereas exponential and uniform distributions are sort of dedicated to specific situations. Normal distributions are extremely useful all over the place. The downside is they have a more complicated looking probability function. So f here is a normal distribution function, and it's given by 1 over sigma times square root of 2 pi times e to the negative x minus mu quantity squared divided by 2 sigma squared. Okay, that's a mouthful. We'll learn what these different things mean over time, but I want to just highlight that there are two unknown values here. There's a sigma that shows up in two places, and that's some number. And there's another value, mu, that shows up just in this exponent up here, and that's another number. So sometimes we'll say that a normal distribution with parameters mu and sigma has this distribution function. We will actually learn what sigma and mu are later during the live session. But for now, those are important parameters that can be tweaked and give you different normal distributions. In practice, this will change the shape of the bell curve, and you'll be able to play around with that on one of the interactive slides. The other downside of this expression, having a complicated density function, is that computing an antiderivative is impossible. So this is one of those functions I mentioned earlier in this course that we just simply can't use any integral techniques to find an antiderivative and use the fundamental theorem of calculus to compute definite integrals. We do know how to approximate things using rectangles and trapezoids. So you can approximate finite areas under the graph of this function. We just don't know how to actually perform the fundamental theorem of calculus on this function in order to directly substitute in and solve for probabilities. So that's the downside. What happens in practice is using all of those approximate values, we can write them down in a big old table, usually in the back of old textbooks, and or you can look these up online, and we can use the values in that table to get accurate approximate probabilities in any question involving a normal distribution. So the main reason that the normal distribution is so widely studied, not just in actual applied problems, but in mathematical statistics in general, is the following theorem. This is really the jumping off point of a lot of statistical analysis. It's called the central limit theorem. And it says that if we choose n independent, identically distributed random variables, so think about this as coin flips, and you have n of them, and they're all identical coins, or something more complicated than that. The average, for example, performing the same experiment n times is like flipping n coins all at the same time. The average of any random variables, their outcomes, will converge to a normal distribution as n gets large. This is kind of a magical statement. We really won't have time to unpack this in full in this class, but this is something you'll learn a lot about in a statistics or probability course later on. What's magic about this is even though we can start with a finite number of coins that have a finite number of total possible heads and tails, as we bump up the number of coins, as we flip the coin more times, in other words, as we continue to perform the experiment, the average of the number of heads or number of tails as an experimental outcome converges to, or the probability of that average being a given value actually converges to the probability that the normal distribution would predict as we increase the number of experiments performed. So another way to say this is, I haven't used the word discrete yet, but when there are a finite number of outcomes, like with our coin and die roll examples, that's called a discrete random variable. As we increase the number of experiments performed on a discrete random situation, the probability, the average probability converges to something continuous, and a specific something continuous, namely a normal distribution. So that's why these are so famous and useful, and they show up everywhere. Okay, so I lied. We're actually going to interpret these briefly here, but we'll actually give some mathematical reasons for this, for the following two statements in class together. But the two parameters, mu and sigma, that I mentioned, mu is actually the average value or the mean of the random variable. And also, this is something that you probably had already heard, so I'm not introducing anything too crazy with with bell curves here, other than having a function for them now. The mean, the average value of a bell curve, corresponds to the peak, the highest point of the bell curve. So this one's centered at 0 in the picture, but in the interactive version of the slides, you can tweak the mu value and slide it to the left and right. That peak will always fall at the mu value, and notice that the mu value shows up in the function. So it's really where you're centering your function is what mu tells you. On the other hand, sigma is the standard deviation that you've heard plenty about, just in statistical terms. Being one standard deviation off from the mean means something, and we'll be able to compute that later. What sigma actually means in graphical terms and in probabilistic terms is the way that the data spreads outward from the mean. So if sigma is larger, then this bell curve will spread wider away from mu and contain more area at a further distance from the average mu. And again, in the interactive version, you can tweak these two different sliders and see how the curve changes. But it's a probability distribution, so no matter what, the integral of this function from negative infinity to infinity is always equal to 1. All right, we're almost done. We're going to learn about expected value, which is, in this case, actually is mu. The average or expected value of a normal distribution is that variable, or sorry, the parameter mu. But for a general random variable, I want to briefly discuss what it means to assign an average value to the variable and then to compute it, more importantly. So the expected value, I'm going to use expected value, average, and mean interchangeably. So the expected value of a random variable x is some measurement that describes what the predicted value is on average. So that's sort of a circular definition. We'll give it a more mathematical interpretation. So we typically denote this by E bracket x. Capital E is not a function of x. X is a random variable. It's just a measurement that you can make on the variable. Or in other words, it's a value that the variable can take on that describes the average value among all possible outcomes. So capital E bracket x is the expected value. Sometimes we'll denote this with mu. And again, mu is the Greek letter for the English letter, or the Roman letter m, which stands for mean. So mu means mean, as in an average value. Here's an example to get your mind around how to actually compute average value. So let's take a fair 6-sided die and roll it some number of times. Let's say we roll it n times. We expect, because it's a fair die, we expect each of the possible outcomes from 1 to 6 to occur an equal number of times on average. So the sum of the rolls will be approximately a weighted sum of each of the outcomes, where we weight the outcome 1, 2, 3, 4, 5, and 6 as our number of dots that shows up on the die according to its likelihood of occurring. So each one has an n/6 likelihood of occurring if n is the number of times that we roll the die. If we want to compute the average of these sums, if we want to compute the average of the individual outcomes, the number of dots that shows up in a trial with n die rolls, then we just have to divide by the total number of experiments performed. So in n die rolls, what's the average roll? We count up all of the possible rolls. That's, again, adding up n/6 times 1, n/6 twos, n/6 threes, and so forth, and dividing by n. Well, that's going to chop out an n from each piece. And we're left with the following weighted average that adds up to 3.5. So how do we do this? The way you might think of doing this is adding up all of the possible sums and dividing by the total number of possible outcomes. In this case, 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the possible dots that can show up, divided by the number of different outcomes. There are 6 of them. That'll give you 3.5 or 7/2. And that's how we compute expected value in general. Add up all of the possible outcomes and divide by the total number of outcomes is the name of the game. How do we do this mathematically? Well, for discrete random variables, the ones that have a finite number of possible outcomes, what we do is we take what's called, again, a weighted average. We have some probability function that tells us how likely each event is going to occur. And then we just multiply that function by the actual outcome so that we're weighting each outcome by its probability of happening. So this is the weight, the probability, and this is the outcome. And if we add all of those up, just like we did in the previous example, the outcome was X and the probability for each was 1/6. That'll give us a value for the expected value. How do we do this with continuous random variables? Well, one nice thing about studying calculus previous to this class is you know that when you take the limit of a summation formula like this, you should get an integral expression. And I'll save us the work here. We're just going to directly write down the following formula. For a continuous random variable capital X with probability density function f, its expected value, e bracket x, is the integral over the entire probability space from -infinity to infinity of x times the probability function f dx. So again, to read this formula back to you, this is something that you'll want to understand and store in your memory for later use. The expected value of a variable is sum or integrate x times the probability function. If it's a discrete random variable, you'll add up each outcome times its probability and do that for every outcome. That'll give you the expected value. For a continuous variable, adding is replaced by integrating. We'll integrate over the entire real number line, -infinity to infinity, of x times f of x dx. I'm going to leave this example as an exercise for you to do. So you should flip back a few slides. You can pause and do this now, or you can do this after the video is done, and compute the expected value, e bracket x, for a uniform random variable on an interval from a to b. I gave you a formula for the uniform random variable's density function in this case, and what I want you to do is compute the expected value using this formula, this infinite improper integral, this potentially improper integral. If you do this exercise, one takeaway you'll see is that the expected value typically occurs somewhere in the middle of the possible outcomes of the random variable. When the density function is symmetric, this is a spoiler for the previous example, this is actually the midpoint. So if you haven't done the example yet, when you do the uniform expected value computation, you should get the midpoint of the interval as your answer. So that gives you something to go verify for yourself. Let's do the next one together. Let's take that exponential random variable and compute the expected value and then explain how lambda fits in. Remember that lambda is how many times per hour some event occurs on average. And the exponential random variable tells us how long we have to wait as a probability for the first of those events to happen. Let's compute the expected waiting time. This is really the key piece of information to extract from an exponential distribution, the expected wait time for some event to happen, given that it happens on average lambda times per hour. And if you're not comfortable with the interpretation yet, let's just pare everything away from the problem. And by the way, here's the formula for an exponential random variable with lambda, that parameter that is describing some number of times per hour we expect. So let's just take this function and say, what's the expected value of this function as an exponential random variable? Forget about all the interpretation. How do we compute expected value? Well, the formula a couple slides ago is we integrate over the entire real number line the function x times f of x dx. Notice that when x is less than 0, all of these values are 0, so the entire integrand is 0. So we can really just focus on integrating from 0 up to infinity. But unlike a previous example where we stopped at 3, we actually have to go all the way up to infinity. There are positive probabilities in this function for all possible x values. If you look at this function closely, it's never 0 again. So I want to integrate x times lambda e to the minus lambda x dx. And this is an improper integral. I don't get to just integrate from 0 to 3, for example. But also, if you stare at this integral closely, this is of the form x times e to the something. And then there's a lambda. Lambda is a number, so it's a constant we can pull out. So x times e to the blank. It doesn't look like I can do a u substitution. This is actually a job for integration by parts. So I'm going to solve this as an indefinite integral, but let me write out the u and the dv first. So u, using late, I'll choose u equals x, so that du equals dx. dv is everything left lambda e to the minus lambda x dx. And that means v is, well, if I had e to the minus lambda x and I took its derivative, it would spit out a minus lambda times the same expression. So I need a minus sign to compensate. But here I'm capturing that lambda. If you're not sure how to go from here to here, you want to carefully do a separate substitution, maybe a w substitution on the side to compute your v. But here's our values. Now that I've given you these choices for integration by parts, you might want to pause the video and try this as a practice problem. Come up with an antiderivative for this. And then after we do that as a separate indefinite integral, we'll go back and solve the improper integral separately. So here we go. The integral of, I'm gonna switch things around because I like my constants in the front. Lambda x e to the minus lambda x dx is given by u times v, that's minus x e to the minus lambda x, minus the integral of v du. So v has an extra minus sign, I'll put it up front. And then du is just dx. And then we stop and say, is this an integral we can solve? Well, sure it is. It's just an exponential. Just have to be careful about the constant coefficient. So we'll copy paste the first expression. Here we're going to get e times lambda x. If I take the derivative, it'll spit out a minus sign. So I need a minus sign to compensate so that I get a plus up here. In any case, this is plus c at the end because this is an indefinite integral. But now let's go back and solve the original improper integral that we were interested in. So lambda x e to the minus lambda x is our probability distribution function. To solve this as an improper integral, we're going to take the limit as the upper bound goes to infinity. And now I have an antiderivative, so I can solve this in this interior definite integral using the fundamental theorem of calculus. So I'll put it in big brackets. I think I'm going to give myself a little more space here for this. So I'll have negative x e to the minus x minus lambda x minus e to the minus lambda x. I'm just pulling this from our antiderivative computation. And I'm integrating from 0 to b, and then I'll take the limit at the very end of the problem. So let's keep our limit symbol out front. That's important. Let's plug in b first of all. So I'll get negative b e to the minus lambda b minus e to the negative lambda b. Good. Minus what happens when we plug in 0. Well, the first expression is 0 because there's an x up front. Next expression is e to the 0 is 1, so I'll get a 1 there. Let's see. What did I? You know what? I made a mistake. So let's actually go back and you might have caught this if you were following along closely. I actually made a mistake in my antiderivative. I just noticed. So let's confirm this computation. Let's show what this true computation should be. So if I guessed e to the minus lambda x and took the derivative, I would have a negative lambda come down. So in order to compensate, I need a negative 1 over lambda. And now this is correct. If you can take the derivative to double check, you'll see that you get exactly that expression in the integral. So I made that mistake. Sorry for that. But let's go fix things in our antiderivative. It's going to show up a few places. I'll just jump back a few steps. So minus 1 over lambda e to the minus lambda x should go here. We're integrating from 0 to b. Now let's just double check. We plugged in b into the first expression carefully, and then we'll have 1 over lambda e to the minus lambda b. And that's, now we're done with plugging in b. Let's also plug in 0. The first expression is still 0. The next expression, e to the 0 is 1, but I'll have a 1 over lambda. Luckily, I did this one ahead of time and I know what the answer is, so I was able to catch my mistake. But in general, if you didn't know what the answer was, you want to just do these computations a little more carefully than I did. We're almost done. Let's evaluate this limit now. So what happens when we take b to go to infinity? Well, exponentials win the race against, this is just a single power of b. And e to the negative large exponent is going to go to 0. Likewise, e to the large exponent is going to 0. So actually what we have left is the negatives cancel out. And we have 1 over lambda. So part B of the problem said, does this make sense? Explain why lambda makes sense, given that it's, the number of times per hour something happens, and the variable here is tracking expected wait time. So the expected value of this variable is 1 over lambda. Let's go back to the 3 times per hour happening. If some event, maybe my alarm going off happens 3 times per hour, but it happens randomly in that hour, what's the expected wait time for the first occurrence of that event? Well, if it happens 3 times per hour, we expect 1 time unit divided by 3. In other words, 1 hour over 3, or 20 minutes for the average wait time for the first event to happen. And that's it. That's what the exponential random variable tells us. We got a couple more things to talk about. Thanks for hanging out for the end of this video. But now we've computed one expected value. I left the uniform distribution as an exercise. We've computed a couple probabilities. Let's start tying things together. Here's a graph of an exponential random variable, by the way. This is with lambda equals 0.75, but our formulas work for any lambda. So you can work this out in given problems or work it out as a formula with lambda as a parameter as well. One thing to note is that for asymmetric density functions, the expected value, the mean value of the distribution, will not be smack dab in the middle of the range of values. It's actually going to be pulled towards regions of higher likelihood. What does this mean? Well, if we think about the x values along the x-axis as being the possible outcomes of our experiment, in this case, it would be the possible wait times for the first occurrence of an event, the possible wait times to get through the line, for example. The expected value is the expected, or the average wait time for the first event to occur. And that is not going to be directly in the middle. Well, I mean, in this case, the interval is from 0 to infinity. And so middle doesn't even make sense. But it's not really going to be in the middle of the values even graphically. It's going to be pulled a little further to the right than you think, because most of the x values occur to the right, even though they have lower and lower probabilities, and the probability decays exponentially as the wait time goes up. But there are more of them still. So the expected value gets pulled to the right a little bit, even though it looks like a lot of the probability is captured by the first part of the graph here. There are a lot of values assigning some positive probability out to the right of the graph. So the expected value is further to the right than you think. Now, that's sort of a peculiar thing because we just learned about expected values. So, why would we have expected something different? So in order to answer that, I want to study this question again. And rather than waiting in a line, let's pretend we're all on the phone, since we're in a pandemic, and we call the call center instead of going to the local shop to ask our question. So if everyone in class is on call with the wait little jingle playing, we want to know what the expected wait time is for a call. This will be modeled by an exponential random variable. So it'll have the same formula with lambda that we just used. And we want to ask, what's the median wait time? And then it'll turn out to be that the median wait time is less than the expected value for the wait time, that EX that we just computed. So we want to understand, why is this the case? And it has something to do with why things got pulled to the right a little bit. So let's do this one together. We have not talked about median so far, but if you think back to whenever you first learned this word, median, you'll probably come up with the following definition. I'm just going to give it to you so we can wrap things up. So the median of an the median of a random variable, it doesn't have to be exponential, it's an x value along the x-axis, and it's the precise value so that exactly 50% of the distribution, 50% of the area under the distribution function lies on either side of the value. It's the midway point where we account for different probabilities. And apparently the expected value isn't the midway point, it's not the median. This should come as no surprise if you've seen examples with median and expected value or average before, that they're not always the same. So here's what we're going to do. Let's set our probability that the random variable lies to the left of our median. I'm going to call the median M. Let's set that probability equal to 50%, or 0.5. So whatever M is, when we compute the probability that, here's our graph. If this is M, we want 50% of the data, or of the outcomes, to occur to the left of M. If we set this up, we can write P of this event occurring as an integral. It's going to be the integral from negative infinity up to m of fx dx. This is actually a method for computing the median of any random variable. So you can do this for the other example. Well, you can't do it for the normal distribution, but you can do this for an exponential distribution. You can do it for that quadratic 1/9 x squared that we worked on, compute its median. But now for our exponential distribution, let's actually plug in what f is. We know that for negative values of x along the x-axis, the distribution is 0. So we only have to integrate from 0 up to some m. And look, we don't have to do an improper integral this time. This is what's nice. And the function is lambda e to the minus lambda x dx. That's our, you can scroll up to see this or flip back a few slides. This is our exponential distribution function. So now we just need to integrate. I think we already did this one. This would be minus e to the minus lambda x. You can double check if you want to. And double check by taking a derivative where you can carefully do the integral. We're going to evaluate from 0 to m. It's going to give us negative e to the negative lambda m when we plug in m, and plus, so minus plus e to the 0 is 1 again. So again, this is equal to 0.5. I'm going to write it as 1/2. Sometimes it's easier to solve for, we want to solve for m. We want to know what the median is. If we make things fractions, in this case, it'll help. So what I'm going to do is I'm going to push the e to the other side of the equation, but I'll write it on the left still. And then subtract 1 minus 1/2, that gives us 1/2. Okay, this is e to the minus is really 1 over e to the positive exponent. So that's e to the lambda m equals 2. And now it's a matter of unraveling this expression, solve for m. I'm going to take the ln of both sides. So lambda m equals ln of 2. And that means that m, voila, is 1 over lambda times ln of 2. So part B of the problem, and this is actually a formula for the median of any exponential distribution. You just decide how many times per time unit the event occurs. That's your lambda parameter. And then the median, so that 50% of the time you're on either side of this x value occurs at this value every time. Part B of the problem said, why is this to the left of the expected value? Remember that the expected value of this variable, sorry, I'll write it as a capital X, was just 1 over lambda. We computed that in a previous problem. So for m to be less than that, that means ln of 2 is less than 1. It's something like 0.69 if you work it out numerically. So 0.69 shrinks whatever positive this number is down to something smaller. So the median is smaller. That means that it falls to the left of the expected value on the graph, which means that even though 50% probability-wise is on either side of the median, the expected value gets dragged to the right a little more because there's so many x values to the right. They're stretching off to infinity, even if their probabilities decay exponentially as we move along the number line. So let's wrap things up with a few observations and summary questions. By the way, here's the graph of that situation. You'll see the median is here. 50% of the data is shaded on either side. And then mu, the expected value, is to the right of that. The punchline here is, for median problems at least, is the median is the value so that half of the areas of the function is on either side of that value. We can compute it by setting the probability expression equal to 0.5 and solving for m, like we just did. And in general, the expected value will be dragged away from the median by large amounts of data that haven't yet been weighted for probability. You can think of the median as accounting for probability and putting 50% on either side. And the expected value doesn't do that. So here's some summary questions for you to read. First, think about the difference between continuous random variables and their discrete counterparts. Discrete, again, means not continuous, sure, okay, whatever that means. It really means that there are only a finite number of outcomes. I want you to reflect on how we use probability density functions to compute probabilities and really what it meant to have a probability density function that would do this for us. So in question 3, specifically, what criteria are needed for something to be a PDF? And finally, how do you compute expected value? I'll throw a 5th question on the list. How do you compute median as well, like we just practiced. Here is a practice problem for you to actually work through all of these concepts yourself. I'll leave this one as something you can do on your own. And that's it. Thanks for tuning in, and I will see you next time for the next video.